So we've learned the law of sines, and the law of sines is very, very useful for solving triangles that are not right triangles. And it works very well if you're given two angles, okay? Obviously with the law of sines, you do need certain information, a certain combination of things. You have to have at least one of the ratios known, either the side length A along with its opposite angle A, or the side length B along with its opposite angle B, or the side length C along with its opposite angle C. You have to know one of the full ratios. But you also have to know two of the angles. Okay, that way you can find the third pretty quickly. And so what we've seen before is that if you have an angle side situation where you get two angles and a side, or you can have two angles and the included side, so angle side angle combination, you can solve solve a triangle very quickly by finding the third angle, just subtracting from 180, and then using the law of sines to find the other two sides. Not too bad, we've seen that now. However, the situation is different if you're given two sides instead of two angles. Okay, so in the case of the SSA, two sides and an angle are given, we're going to have a little bit different situation. It's not going to be solved as easily. We're still going to solve it using the law of sines, but it's going to be what we call the ambiguous case, which just means there's many options, right? If a word is ambiguous, we say that it, if it has an ambiguous meaning, the same word could be used to express multiple different ideas. It's ambiguous, right? And in this case, the SSA scenario, two sides and an angle are given. We could have actually the potential for 0, 1, or 2 different triangles that are constructed from that information. Okay, so there's a lot of options. That's why it's called ambiguous. So I've got an example up here. This example has angle A at 40 degrees. I drew it in, tried to draw a roughly 40-degree angle. Side B is 10 feet, and side A, I'm going to throw a value in for side A. We'll see what happens, and I'll throw some other values in. Let's start off with side A being just simply 1 foot. Okay. Now, from the triangle that I drew up here, you can kind of tell if I were to take side A and attach it here, which would have to be opposite angle A, so it'd have to be up here between C and B. Well, B is going to be along this bottom line somewhere. So side A is going to be up here. Now, I don't know what angle C is, but remember, I should be able to solve this with just 3 pieces of information. So I shouldn't need side C. That should be one of the things I can find. The problem is with side A being only 1 foot, it's not going to reach the other side. The other side here is fixed because of my 40-degree angle, right? And so if this is just 1 foot, there's no way it's going to reach all the way down. There's a certain minimum number of feet it can be to even get down all the way. Well, and think about that. What is the minimum distance between a point and a line? Well, it's the perpendicular distance, right? So if you were to find that perpendicular distance, you would have the minimum, so that anything smaller than that would automatically be no possible triangle. We can find that minimum by finding that perpendicular distance. We'll call it h. Okay, there's h. Now, how do I find h? Well, h comes from the sine of A, right? I know that the sine of A, because this is perpendicular, forms a right triangle. The sine of A is equal to h over b, right? If I multiply both sides by b, I know that h is equal to b sine A. And if I take my B and my A and plug them in, that would be 10 times the sine of 40 degrees. And I can throw that into my calculator real quick, make sure you're in degree mode. 10 sine 40. Oops. I accidentally tapped an extra button. There we go. 10 sine 40 is approximately 6.4 feet. It's actually a touch over 6.4. All right, so anything 6.4 and less, essentially, with some rounding there, won't work. It's going to be too short. It won't get down all the way. So this height is approximately 6.4 feet. Okay, so anything shorter than 6.4 will create no triangle. All right, so with 1 foot, the answer is no triangle. So if I gave you 5 feet, for instance, right there, instead of 1 foot, it wouldn't have been as obvious, but it still would make no triangle because that 5 feet doesn't make it all the way down. And no matter what angle I swing it on, it's always going to miss, okay? Just like the 1 foot, no matter what angle I swing that on, it's still going to miss. It's not going to be long enough. So you have to get at least 6.4 feet here, okay? Now the question is, what's the maximum? So obviously anything greater than 6.4 is going to work. What's my maximum? Well, technically there is no maximum, because depending upon how wide open you open angle C, if you had a side A that was 100 feet long, for instance, it would come way out here, but eventually it'll hit our dashed line, okay? But there is a weird situation where there might be 2 possible triangles. Let's say, for instance, I had a side A that was greater than 6.4, so it definitely comes down and hits, but it's less than 10 feet. So somewhere between 6.4 and 10. Let's say you had an 8-foot length, okay? We'll do that one. Another color. Actually, I'm going to keep this 1 foot here. I'm going to make that red. Okay. Now let's do 8 foot. So same first 2 pieces of information, but now A is 8 feet. Well, at 8 feet, you will actually get this to come down all the way. It's going to be down far enough to hit, okay? But if you were to swing it the other way, it's actually going to hit a second time. And so there are 2 possible triangles, one with an obtuse angle and one with an acute angle at B. B could be either of those 2, at either of these 2 spots, here or here, okay? And so there's actually 2 possible triangles. So with A, you have 2 possible triangles, one with an acute angle at B and one with an obtuse angle at. Okay, so those are our 2 possibilities. So we actually have to solve for both of them. So you're going to have 2 possible triangles to solve for, and 2 answers really, or 2 sets of answers. Okay, so let's go through and try to work this out at 8 feet. Okay, well, let's get rid of some of this information. That's good. So let's go with the acute angle first, just because I listed it first. The acute angle, the acute B, is going to be formed. It's a smaller one, so it's going to be out farther to the right. There's angle B, angle C, angle A, side A, B, and C, respectively. Okay. So there I've created the triangle. I know that B is 10 feet. I know that A is 40 degrees, big A, and I know that little a is 8 feet. Okay? Now from there I can use the law of sines, right? I can use the law of sines, and I know that I'm going to have to use the fraction with the a's because I have both of those pieces of information. So I'm going to use a over sine A equals, now I want b because b is the one that we have filled in. I don't have either of the c's, so I can't use that ratio at all. So I'm going to use little b over sine of big B. And big B is the thing I don't know. I just know it's acute for this. So I'm going to fill in the rest. I have 8 over the sine of 40 equals 10 over the sine of B. Well, to solve this, I would cross multiply and then divide out and solve. So I cross multiply first. This is going to be 8 sine B equals 10 sine of 40. I'm going to divide out the 8 on both sides. And so then the sine of B is equal to 10 sine of 40 all over 8. Well, that's simple enough. I can punch that in my calculator. But before I punch it in the calculator, I want to take care of this sine. I don't want sine of B, I want B itself. So I'm going to use the inverse sine. Okay? So the inverse sine, B is going to be the inverse sine of this expression, 10 sine 40 all over 8. You got to be really careful punching that into a calculator. Okay? So I'm going to punch in inverse sine of 10. Now maybe I'll show you this as I go here. If I can get that on there. Focus? It's not focusing well. Okay. Inverse sine of 10, and then I'm going to punch in sine of 40, parenthesis. So I've got that so far. I don't know why that won't focus well. Divided by 8. Got all that. Hit another parenthesis. So all that stuff, that big fraction, is inside of a set of parentheses for the inverse sine. And that should give me about 53.5 degrees. Okay? That is an acute angle, so that works. Okay, so this is approximately, what did I say, 53.5 degrees. All right, so I have an approximate angle there. Now, I chose an acute angle, right? We'll go back and we'll come back to the obtuse angle, but the obtuse angle comes from an interesting fact about the inverse sine. We'll talk about that in a minute. Okay, so I've got B as this acute angle. Now I've got to find angle C and side C. Well, angle C comes from the angle sum formula. So if I take 53.5, add it to 40, that's 93.5, and subtract that off of 180, so angle C is 180 minus the sum of those two, which is 93.5. And that should give me an 86.5 degree angle. Maybe I'll just double check that. 180 minus 93.5, 86.5. That would be it. Okay, so it's an 86.5 degree angle. So I've got two of my answers, and of course I'm just rounding the nearest tenth here, not being too particular about significant digits or anything. And now, using this information, I can find side C again using the law of sines. Okay, so I've got, let's go with the A's and the C's this time. So I would take A over sine A equals C over sine C. And then I'm going to plug stuff in. So I'm going to get 8 over the sine of 40 equals little c, which I don't know, over the sine of 86.5 degrees. Okay. And so here to solve, I'm going to multiply both sides by the sine of 86.5. Okay. And should be able to just punch that in a calculator and get a good value for little c. All right. We'll just round that to the nearest tenth of a foot as well. All right, so I'm going to punch in 8 sine 86.5 divided by the sine of 40. And that's 12.4 roughly. Okay. So this gives us a C value of approximately 12.4 feet. That should work out nicely. That's our side C here. It is the longest side of the three. Notice the longest side is opposite the largest angle, and the shortest side was 8, which is opposite the shortest angle, and the medium side, B is 10, is opposite the medium angle. Okay, so that all falls into place relatively speaking. Okay, so now the next thing I want to show you is what happens when we deal with the obtuse angle. And how do we get the obtuse angle? I already solved for B using the inverse sine. Well, remember, the inverse sine only gives us outputs in the first and fourth quadrants. But, based on this diagram, you could have an acute or an obtuse angle. An obtuse angle is a second quadrant angle, not a first or fourth. And so I'm not really interested in the output from the inverse sine. I'm really interested in the second quadrant, the similar angle in the second quadrant. So I'm going to go ahead and summarize these items over here. So big C is 86.5 degrees, big B is 53.5, and little c, we'll put 12.4 feet. And of course I should make those approximate, but I threw equal signs on there. Now everything else is basically the same up to this point. And then what we have to do is we need the corresponding angle in the second quadrant. So if I know that 53.5 degrees is a first quadrant angle, then in the second quadrant, same thing, 53.5 degrees up would be 180 minus 53.5. Okay, and of course, if you punch that in, you should get, what's that, 26.5? 180 minus 53.5. Did I forget my 1? I did. It's 126.5, my bad. 126.5 degree angle. That's obviously obtuse, right? 26 degree angle is not obtuse. So yes, I have an obtuse angle now at B. So this would be the new B value for the obtuse angle. Then I can use that to find angle C. All right. Angle C is found by taking 180 and subtracting off my new angle B with the original angle A. 126.5 and 40 is 166.5. Okay, and when I do that subtraction, that's going to be what, 13.5? Okay. Should double check that. 180 minus 166.5 is, yeah, 13.5. Okay. So that's good. That gives me a second angle, or a third angle, I guess that's the third one. Now the only thing left, I've got B, I've got C. The only thing left is going to be little c. So little c I can find using, again, the law of sines. We'll get rid of some of this. Let's see, so I'm going to have A over sine A, which is 8 over the sine of 40, equals, what's C? Where is C? Oh, C, I don't know. Ha, that's why I'm not finding it. We don't have it yet. Over the sine of angle C, which is 13.5 degrees. So now I'm going to multiply both sides by my 13.5. There we go. And that should get us a value for C then, approximately. We punch that in. That is 8 times the sine of 13.5 divided by the sine of 40. It's approximately 2.9. Okay, so it's a very short side over here. So if I get rid of some of this extra information and draw this out, the obtuse angle, this is obtuse B, the obtuse angle is going to be the 126.5 degree angle, and angle C up here is 13.5, so that's nice and small angle up there. And then our short side here is, what I say, 2.9 feet. This one's 10, and then A is still 8. Okay. All right, so that should give you all the information about the obtuse angle and the acute angle B. So both options, 126.5 degrees, C is 13.5, and little c, we'll call it 2.9 feet. Okay? So again, two different options for the same given information. So 40 degree angle, 10 foot length, and 8 foot length could end up with two possible triangles, and you've got to solve for both of them depending upon the scenario. Okay? Maybe it's obvious from an application problem that you need the acute versus the obtuse, I don't know. But generally speaking, if you're just given these three pieces of information, you're going to have to solve for both of the other triangles, the acute version and the obtuse version. Okay, now, there is a table in your textbook. It's an important table on page 306, kind of outlines all these different possibilities. Okay, the possibilities, and now I'm just going to summarize a few things. So I'm going to erase some of this work. I don't want to erase a lot of signs. And we'll redraw that. Okay, so the possibilities, if, now I'm going to assume that angle A and side B are given, and then it's side A that we're going to be comparing. If A is less than H, then no triangle exists. That was our first scenario here. The A value was smaller than that H, the perpendicular. And when that occurs, there's just no triangle. Okay, it doesn't matter. It's just not going to have one. It's not going to be able to reach down that far, right? Okay. So that's pretty much always the case. If A is equal to H, So if I were to give you this opposite side here, and it is actually exactly the height of the triangle, that height h, then one triangle exists, and it is a right triangle. Okay, so if A equals H, then there's only one that exists, and it's a right triangle. It's just this triangle with the red side on it. Okay, that is a possibility. In the event that A, this other side here, is actually longer than B as well. It's not only long, so it's longer than H, but also longer than B. Then it's going to come way out here. There's only going to be one triangle, and it's a big triangle, right? If you tried to swing it the other way, it would go outside the triangle, and it wouldn't exist. So there's only one option. So if A is bigger than B, actually I'd say bigger than or equal to. If it's exactly the same size as B, you wouldn't be able to swing it the other way either. So that's an option. So if A is greater than or equal to B, then one triangle exists. Okay. And then the other option is what happens when A, and this is the one here, where A is in between the height and the B value, when it's in between those two. And in that scenario, you end up with two triangles, one with the acute angle, one with the obtuse angle. So if H is less than A, which is less than B, right? So A is in between H and B. H less than A less than B, yep. Then two triangles exist. One has acute B and one has obtuse B. Okay, so one has an acute angle at B and one has an obtuse angle at B. Those are the two options. Okay, so this all exists, this all occurs when your A value, the angle A, is acute. All right. Now you get a very different scenario if that first angle, the given angle, is itself obtuse. If that opens up obtuse, then you either have the scenario where no triangle exists, okay, or you have a scenario where only one triangle exists, right? If angle A was obtuse already, you couldn't have a situation with both an acute and an obtuse B. Excuse me, because you can't have two obtuse angles in the same triangle. Okay, so that wouldn't work out. So you just have to be careful there. If angle A is obtuse to begin with, greater than 90 degrees, then you have fewer scenarios going on here. Okay, in those cases, let me erase some of this and draw that out for you. In the event, there's angle A, and C is up here, and B is along this side, then if this is A, if it's too short, it won't get all the way down. Basically, side A has to be longer than side B in order to have any triangle at all. So if A is less than B, you don't have to worry about the perpendicular side this time, because that doesn't matter so much. It has to be longer than B in order to get down to the other side. So if A is less than B, then no triangle exists. Separate those off there. And if I guess if it's longer than A, Oh, yeah. If A is less than B, then one triangle exists. And that's it. Those are the only two options. So you just compare the A to the B value, and that's going to be good enough. You don't need the H to be factored in there. Okay, so we'll try a few more examples in the next couple videos, but overall it's kind of a good picture of what you might see. And these things are summarized in the table in your book on page 306. It gives some diagrams along with the inequalities and the different conditions.